Welcome, my digital pathology trailblazers. Today we're going to be talking about different tests, statistics.
Learn about the newest digital pathology trends in science and industry. Meet the most interesting people in the niche and gain insights relevant to your own projects. Here is where pathology meets computer science. You are listening to the Digital Pathology Podcast with your host, Dr. Alexandra Zhurov.
And we're going to explain and model evaluation concepts that are so perfectly explained in this paper, in addition to all the metrics. So you can check the tables. I went through the tables and I learned about metrics that I have never heard about. So you can do if you want to, but we're going to be discussing higher level concepts because my goal with all these courses, all these videos is to bring you to the level where in a digital pathology team, in a computational pathology team, you have all the knowledge that you need to be able to contribute immediately and have productive, good scientific discussions with your co-members, and different team members are going to have different expertise. My is toxicologic pathology, right? So I'm on the pathology end. There may be other pathologists, there may be computer scientists, there may be software developers here. And we are going to be all at the same page so that we can bring digital pathology forward. The topic of today is statistics. So fundamentally, we always, in the series, we talk about generative, non-generative AI, and these two categories, different metrics. And after we go through this introduction, we're going to go to the images. So don't worry, generative and traditional, also known as non-generative predictive analytics. And there are a couple of synonyms, but basically generative that creates something new, like the text, and the classical, which calculates, predicts some analytics, right? And they rely on certain common statistical measures of function. And there are some that you will know the more classical because this is like in any lab test and we're going to dive into them. But there are some new ones that are going to be applicable to the generative AI, like Perplexity. Do you know this software, Perplexity? It's a search engine, retrieval augmented generation-based search engine. I love it, my best friend. But love but verify. That's the overarching message. So I did have to check some sources. Anyway, bilingual evaluation, understudy score, and other different ones. And these are less familiar because these methods are new for us. So we need to familiarize ourselves with that. The classification-based one are confusion matrix-based, and I have a little confusion matrix that I drew for you. You will recognize instantly, even if you don't know the word confusion matrix, you will know what I'm talking about. But everything has heard about accuracy, sensitivity, F1 score maybe, or dice coefficient, receiver operating characteristics area under the curve. And some of you may have heard about regression studies like root mean square error and R square. So I highlighted this word here, better stewards. That goes with what I just said, that this is our responsibility to know how to test this stuff. I'm the first person who has to check herself after being super enthusiastic about a new model, new method, new whatever, right? Love but verify. So by understanding these similarities and differences of these different metrics, we become better stewards of this transformative space of digital pathology. This is part of digital computational pathology. And if we want to be digital pathology trailblazers, we need to know that. So without further ado, let's check where we are today. First, we're past halfway mark. We have 3 more to go. And then we're going to be back to our regular abstract reviews, or maybe, some additional paper reviews. If you have suggestions, let me know. But we are statistics and ML, machine learning in medicine. So in the paper, you will find amazing graphics, amazing tables. If you don't have time to read the paper, just go through the tables and graphics. So in table 1, we have the common generative AI performance measures. So there is a list We have the name of the measure, the basic description, the key points, which I have a beautiful heart here because this explains you the limitations. So like in the story at the beginning, the limitation of data from your training set is that it's going to be very high scores, right? Because you trained on it. So it's totally overfitted. And then there's type of data assessment. And this is generative AI, so most of it is going to be text. But we also have some stuff for image, GIS, and image and text. So I'm going to mention them, and then based on some graphics, we're going to dive deeper into them. So we have Perplexity. We have a bilingual evaluation understudy. This is the BLEU score. Recall-oriented understudy for gisting evaluation. That is the ROUGE score, WER. Metrics of evaluation of translation with explicit ordering, like stuff I had no idea existed, but that's okay because now we know it exists. Consensus-based image description evaluation, SPICE, which is semantic proportional image caption evaluation, ELO, FID, IS, SSIM, that have names that we will look at later. But basically, you have a mean opinion score as well, and the DICE similarity coefficient, which is very similar to something that we're going to have in the next table. This one is used for segmentation. And in this table, you go through the table, like let's say you have a model, you go through the table and you check, okay, which one fits best? We have different measures, we have description, we have the limitations. So for example, Perplexity is not intuitive and is difficult to interpret absolute values. Is this going to be a good metric for our use case or not? Bilingual evaluation understudy does not consider recall and insensitive to meaning and concept. If meaning and concept are important, then that's not going to be a good metric, or you can combine metrics, right? So these are the things that you can use for generative. And when you look at the output, and for the different data categories that we had image, we had text, and we had tabular data, right? So here for generative AI statistical assessment methods, for the outputs, we have image and we have text. And here we have a list of what can we use for image. We can use FID, we can use Inception, SSIM, MOS, and DICE. DICE is for comparing masks. This is something you may have heard about for classical computer vision stuff, where this is the thing where we compare annotations against the masks of the model. So the model against ground truth generated by a pathologist or a subject matter expert. Text, if we are dealing with text, we have a different set of metrics. We have the BLEU, we have the ROUGE, we have BERT score, BART score, Panda LM, Meteor, Perplexity, right? So my message here is, even if we didn't dive into the scores, there are specific metrics for a specific output, for type of model, generative versus non-generative, and we need to figure out which metric is good. So accuracy doesn't cut it anymore. And actually, this is the example that people always give. Especially if you have unequal data distribution, and for explaining test results, like high accuracy. Okay, if you have a set where there's one diseased person and the model in 100 samples, one diseased person, and the model says everybody is actually healthy, then it's 99% accuracy, but you totally missed the sick person, right? So each of those metrics has those limitations that we have seen in the table. And you need to know what the limitations are and which metric to pick. And for image, we have these green ones. For text, in generative AI, we have the orange ones, right, that we just mentioned. So let's dive a little bit deeper into some of the generative AI statistical assessment methods. Let's focus on Perplexity. So perplexed is like confused, right? So the least confused you are, the better your score, right? So that's why low Perplexity score is the good score, whereas high Perplexity is the bad one. So you want perplexity to be low. So we have training data, prior text, and you can see that this is like the dotted lines. And when you check the perplexity score, this has dotted lines. The high sample output matches original well has dotted lines on the image, and the sample output that matches original poorly doesn't have dotted lines, it has stars, so it is dissimilar from the training data, meaning it has high perplexity, high like is very confused. It is less likely to produce, and I cannot say confused because all these, I can say whatever I want, right? But my point here is that in this context, different common words have a specific meaning because they correspond to a statistical metric that can be calculated. So perplexity has a common language meaning, but it also is a score. The same with confusion. Anyway, I know you get what I'm trying to explain, but here, low perplexity score is actually good. Why did they put it in red? They should put it in green or something. Blue always is like more positive than red. And the model is more likely to produce the next word at each stage of generating a whole output, thus giving the right output. And there's going to be a lot about this model generating next sentence, model generating coherent text, model basically creating something that makes sense. And this is what all the generative AI metrics want to convey to us. And there are different ones for different things, right? And you probably need to combine. So that is perplexity. Let's move to BLEU and ROUGE score. We have human written text. This is our human written text. We have a totally different understanding of ground truth now. It's not going to be the classical annotation, the classical showing which cell it is, because we're working with text, and we are gonna do comparison of original text to AI generated text. So, and in those two scores, here the AI generated text with similar fluency and syntax. Like, how do you even quantify fluency and syntax? That is like amazing that you have to do it now, right? So maybe you can like even apply those scores to grading human generated text, like high school papers or something. So if we have good score, the scores are good, then the AI generated text is similar to what we had from the human. And then if it's not a good score, then AI generated text is dissimilar. It doesn't have dissimilar fluency or syntax. So it doesn't even say like correct, incorrect. It's just dissimilar from what was there originally. So these are the BLEU and ROUGE text comparison methods. You basically compare text, right? Our next candidate here is called next sentence prediction accuracy. And I put this little note here. Is it logical, coherent? This is what this metric is about. So it predicts, it checks if the next sentence after a certain sentence makes sense. So let's say we start with sentence A. It's going to give each of these sentences a score. And this one is very high, right? So the score to predict the sentence G would be higher than if it predicted sentence H. And just for those who are listening to this and not viewing, it's figure 3 in the paper. We are discussing figure 3, so you can listen to stuff and look at the paper as well. So if the desired sentence combination would be A and G, this model would have relatively good sentence prediction accuracy. However, if the desired sentence combination was C, and C on the left hand is like very low, below 0.2, and H, here we had the H, then it would have very bad next sentence prediction accuracy. The good thing about this is that the name of this metric actually tells you what it does. And like summary of this, is it logical and coherent? Is the next sentence, you give it a sentence and it's supposed to predict the next one, is it logical and coherent? If it is, good score. If it's not, bad score. And we can apply also different metrics to images. And images are always more complex than text. Well, it depends. Sometimes they are less, sometimes they're more complex. But we have these FID and SSIM score. So SSIM is Structural Similarity Index Measure, and FID is Frechet Inception Distance. And these metrics are used to evaluate the quality of images, especially those generated by models like GANs, generative adversarial networks. So SSIM, Structural Similarity Index Measure, and Frechet Inception Distance. So in normal person language, the FID is comparing features of the image to the original real image, whereas the SSIM is comparing the perception. So like luminescence and those like image qualities comparing to the real image, whereas here is features. And on the left, this is still figure 3. And in this particular graphic, I don't see the differences between these images because it's a very small histopathological image. But the point is that if the SSIM is high, it's good. And if the FID is low, it's good as well. And then the image is similar. Whereas if these scores go in the opposite direction, SSIM goes down and FID goes up, then the images are dissimilar. And how does this apply to generative adversarial networks? So you have a combination of two networks where one is checking the output of the other one with those scores, or probably some other scores as well. But basically the point here is you have the real image and you compare output of a network or of a model to this real image on different levels, on the feature level and on the image property similarity level. So like, contrast, luminescence, colors, and all the stuff that you basically see but don't even think you see. And these are what those scores are about. One more that is pretty cool is the masked language modeling accuracy. So what's happening here, you're masking, this one is easy. You're masking words. Let me show it to you. So we have an original sentence. The scariest predator that humans can encounter in North America is the bear. Okay. And then we mask. We cover some words. And the new sentence is, as you can see on the screen, the scariest that humans can encounter in is the bear. Something scary in somewhere is the bear. And then AI model is supposed to fill in the blank. So obviously, if the model says mask 1 is predator and mask 2 is America, it did a good job. Whereas if it says herbivore and Antarctica, it didn't do a good job, right? So that's a cool one too as well. But what you see here is that these metrics are totally different from what we were used to from the classical computer vision. And we are moving to table 2, which is gonna tell us, and we're gonna go through them very quickly just to mention them, just that you have heard the names, which most of them you probably know already because this has been around for longer than the generative AI, are the non-generative AI statistic metrics in classification. But actually, before we dive into, I want to show you something that I forgot to show last time. The book, Classification. Do we have classification here? Like specifically. I'll come back to it. This is the computer vision to pathology vision translation. Like, what do you actually do when you detect objects, when you do semantic segmentation, and that you need different metrics? That's from the book. If you don't have the book yet, which I suspect most of you have, but you can get it right now you can scan this code, and that's going to be a free ebook, my free ebook, Digital Pathology 101, where you will find this image on page, which page is that? 84. So if you want it, grab it, but we're going to go back to the paper. Okay, so common non-generative AI metrics. We know, so they are confusion-based metrics, and I'm going to show you my confusion matrix. I drew confusion matrix for you because they didn't have confusion matrix image in this paper, which I guess it's maybe like too basic, but you will know this super well if you have ever evaluated or learned about test performance, not just AI performance, but any test performance. Confusion matrix. This is confusion matrix. This comes off true positives and false positives. So TP, true positive, FP, false positive, TN, true negative, FN, false negative, right? And we have the actual values and the predicted values. So if our model goes and classifies or says that a true positive is actually a true positive, then we have plus and a plus, it gets a green color and it lines up on a line. And these confusion matrices can like grow a lot because you can have a lot of classes, and for every class you have a prediction. But the prediction comes down to, is it a true positive or is it a false positive? Is it a true negative or a false negative? So all the other metrics are based on this, all the confusion matrix based metrics. There are other ones that are regression based, which quantify, like in general, how much error a model is making. But what it comes down to, accuracy, sensitivity, specificity, F1 score, everything that we have in the table is, okay, is a true positive classified as a true positive? Is a true negative classified as a true negative? Yes, no, how many of these are classified correctly? And there are different combinations of that. So let's go back to our table. Sensitivity, specificity, balanced accuracy, ROC, AUC, and the curves. And you have, not only do you have the description and another name, because they of course have different names. It is this, okay, is it, it is super important information. Is it prevalence dependent? So accuracy, where's accuracy? It should be precision or positive predicted value. We don't have accuracy here. Is, for example, precision, positive predictive value is prevalence dependent. So you're going to check, okay, what is the prevalence of the disease or whatever, the feature, whatever I'm classifying or looking for. If it's dependent on prevalence, then maybe we need a different metric, or we need a combination of metrics. That was the example where I said, okay, there's just one diseased person among 100 people. The positive predictive value, if you say everybody is healthy, is going to be very high because you only have one diseased person. And there are different combinations of this, like fallacy. Then precision is positive predictive value, negative predictive value. Oh, we have accuracy, of course we have. And yes, it is prevalence dependent, right? This is so useful, guys. Like, this table is useful. Like, if you're working with it, just print it out and paste it on your, I don't know, your board or wherever, because that's something, if this is not your day-to-day, which if you're like me, it probably is not, but you need to know it. And I knew it. Like, every time I studied, I know, but then I forget about it. I don't know what else is like that. But these metrics, like, I've given presentation on them, super comfortable, confident, and like very, like, I knew what I was talking about. And down the road, I forgot. And then I had to, like, with this table, you don't have to do the searching anymore. You already have all the information that you need to pick the right metrics. Or if somebody's like giving you metrics, performance metrics of something, you can go to this table and check, okay, did they prevalence dependence? What are the important points, right? And all these other things. F1 score, that is pretty similar to the dice coefficient, but dice coefficient is being used for images. and then MCC, also known as coefficient, that checks the correlation coefficient, that is the correlation coefficient between observed and predicted by classification. So this is also important by classification. PRAUC, calculated from various recall, sensitivity, or true positive rate and precision values. So you have combination of all these metrics that are mentioned in table 2, and this is a gift from the authors to us. Thank you so much. Yeah. Monica saying we all go through this, through the confusion matrix of confusion matrix. Okay, thing is listed there. This is fantastic, but there, so that a lot of it was confusion matrix based, so the true positives, true negatives, false positives, false negatives. If it has anything to do with that, it's going to be confusion matrix based, and that will be the metrics that you're going to be using. And ROC AUC curve is an example of that. There is another option, a regression based metrics, and these basically calculate the error magnitude. How much does the output of model differ from what it was trained on? And the goal is to minimize the errors, but this is a lot less granular. So like it's more overall performance specific metrics that you want to know. So stuff to remember, you can do for classification, we have confusion matrix based metrics for regression based, right? So checking how many errors has the model made. And now in figure 5, let's compare the traditional and non-generative AI methods and their statistics. So this is super cool. But figure 1 is gonna compare the benefits and drawbacks of predictive analytics for traditional machine learning, generative AI. So let's just quickly go through this. I want you to hear it. You can feel while we're reading this. The predictive analytics for traditional machine learning, non-generative, since the outputs are simpler and we know what is going on during data generation, interpretability of the data and its validity becomes much clearer. Very good at providing precise prediction, specific, well-defined tasks. And what is not so great is limited scope of outputs due to following human programmed rule sets and an inability to learn from previous experience. But that's a drawback. And also noisy or incomplete trained quality can lead to inaccurate predictions and classifications. That is across the board. You have bad data results. And statistical methods, these are the confusion matrix based, accuracy, precision, and everything we talked about, recall, sensitivity, and regression. So, okay, the first decision you're going to make, okay, are we doing confusion matrix based or are we doing regression based? And points are that they have greater interpretability, and this ties back to the category itself as well as to the statistical methods. So the predictive analytics, they have greater interpretability. So the metrics of the predictive analytics are gonna have greater interpretability as well, right? And the thing here is, and we have plenty of them, they cannot always capture the full complexity of nonlinear, multifaceted data, which is more common in real world. And since humans are designing aspect of the model and statistical analysis, we introduce our own biases into the process, which is not limited to the predictive analytics. It's probably like a feature. It's not feature. They always say it in the software development world. Actually, it's our feature. We are biased by our experience, by our education, and by everything. This is what we like carry inside of our head. And this then translates into everything we create, including designing statistical analysis and statistical performance metrics for predictive analytics, right? When it comes to generative AI, there is wider range and scope of outputs due to being able to iteratively learn, and therefore presents greater possibilities. Can augment existing data sets. This is cool. For better research or training outcomes. And it's better at capturing complex patterns and relationships within text. You can analyze text, you can summarize text. It's not just like matching ground truth. The problems here are difficult interpretability and verification of validity. The generative processes are very complicated black boxes. So we have AI, we have the black box component that we cannot fully explain, even though we're working on explainable AI as a science method or like as a part of AI. But the Gen AI is even more complex. And then obviously poor training data quality can lead to unrealistic, biased, or harmful output. That's across the board, and greater privacy concerns due to the immense capabilities and ability to learn. And ability to learn is something that like kind of frozen. It's not that like the models that we're using, ChatGPT or Claude or whatever, when you are inside of the user interface, that they are constantly learning. You can iterate with them with different prompts, but to train this model and make it better, you have to like start the training process. And there is an option to that for privacy reasons I opted out from in ChatGPT right now is, oh, do you want your like interactions with this chat to be used for further training of this model? And I said, no, like I don't want it. But it's not something that's happening in real time. It's something that the developers use like new data that you're generating to later train the model. And the statistical methods that we have mentioned were ROUGE score, BLEU score, FID, SSIM, MLM accuracy, Perplexity score, masked language modeling accuracy, next sentence prediction accuracy. So everything like checking, does this text, most of it is still text, make sense? And sometimes these methods appear to be valid, but are in truth prioritizing superficial data similarities over meaningful relationships. So like if data is superficially similar, it will have high scores rather than meaningful relationships. So that's a problem, something you have to consider. Highly sensitive to data quality issues. Minor flaws in training data lead to bias per quality and output. That is a problem across the board. And value of these things is challenging, right? You don't have a number. You cannot put the threshold, oh, above this and that positive predictive value, it's okay, because that's not a metric you would use here. So validating this is going to be an interesting endeavor. But let's discuss this figure 6, which they always have this like looking into the future. And basically they discuss different metrics in the paper. You need to choose the right metric for the right use case. All of them have limitations. So the solutions to generative AI statistical limitations is to maybe create large language model-based assessment platforms, integrate large language into scoring solutions, assess performance based on coherence, fluency, and relevance, right? Not just like data similarity, not just sentence similarity. And human expert assessment platforms enable experts to review and rate generated samples. So this human in the loop concept, which I'm a fan of, because you cannot always predict everything and a person will be able to catch it. So you can enable it to review and rate generated samples, provide high quality human curated evaluations, and then in the future you can automate this process to scale, because obviously if you have human in the loop all the time, and we know this from the annotation examples, it's not scalable. And then also something called adversarial testing. You train an AI to evaluate an AI. So maybe that is part of, right, adversarial testing, like the general adversarial networks, where one network is checking the output of the other network. And once they are on the same page, then maybe then you show it to a human, or however you want to design it. The goal is to create robust and reliable evaluation frameworks to improve model performance and trustworthiness in generative AI applications in medicine. Yeah, improve model performance and trust. That's what we want. Whereas when it comes to solutions to traditional ML, non-generative ML statistical, we can use something called Ensemble methods, where we combine prediction of multiple models, improve performance, improve accuracy and robustness of classification and regression models. Then the challenge that is data drift, we design data drift assessment identification, improving machine learning operations, and then we can also do secondary and tertiary generalization testing to minimize overfitting issues, and enhanced model transparency ties back into the explainable AI and the abbreviation. This is actually an official abbreviation of explainable AI. The goal here, so identification of feature importance to minimize explainability issues, and the goal here is to develop a reliable AI integrated system for performing the statistics associated with traditional machine learning, for example, classification and regression models. Other than that, if you have any questions, let me know in the chat, let me know in the comments, reach out on LinkedIn, and I will talk to you in the next episode.